Thank you everyone for coming. Thank you to the jury for coming especially. And thank you to the chairman for those nice words. Thank you for pronouncing the long title so I don't have to do it again. Thank you to my friends and thank you to my colleagues, my business partners, and everyone who found the time to come by here. I just need the mouse here. Okay, so I will be presenting a lot of slides in not very long time, and there will be a lot of stuff on it. So I hope you won't be overwhelmed, but now I warned you already. This is an industrial PhD as a partnership between DTU and Niros, a consulting engineering company in Denmark, and it's funded by the Innovation Fund in Denmark. So the agenda for today will be first, I take you through the practical point of departure, like what motivated me to do this. Then I'll go through some theoretical stuff, the research problem, BIM, building information modeling, and something about link building data. Then I'll take you through a research design where I present you with the research questions, my methodology, and research tasks. Then to the results. And then finally, I go back to these research questions and I talk something about the contributions to academia and industry, respectively, some future outlook, and some final words. So basically, what are the experienced problems? Is it recognized, and are there any solutions? Based on these two, how to progress, and what are the key findings? And now, are the problems then solved? Okay, so first some characteristics about our industry. We work in an industry with many different stakeholders with different backgrounds. The building client, the building owner, the architect, and the technical designers, engineers. We have many design iterations. The client's requirements change, and then the design needs to adapt to that. Then we work in a very document-based manner. If I need to find a piece of information, I need to read through a 50 pages report to extract that piece of information. That also means that I gain a lot of knowledge on the project, which also means that I become an indispensable information source over time, which is good if you're in a company that has a lot of good workers. But the problem is that right now, for instance, we have a very high employee turnover, meaning that essential knowledge is lost from the big projects. And the problem is that over time, actually, these big companies we have, consulting engineering companies, they don't grow very much compared to how the workers evolve. I have a few examples. This is a project called Axel Towers in central Copenhagen that I was part of. And when you design a building like this, HVAC design is highly dependent on the geometry of the spaces and the functional requirements of the different spaces. Okay, so that's good. But what when the space functions swap all the time, and when spaces merge, and when walls that move around? You know, how do we deal with this? In the current situation, if you ask some engineer what he needs in order to do a heat loss calculation, he would say, I need the latest architectural drawings. But what he actually needs is something like thermal requirements of the rooms and usages of the rooms, and then some properties related to the geometry. But the way he's receiving that today is through PDF documents. There's no link between it. Then he puts it into a spreadsheet, and that's good. We usually ask the student worker to do so. It takes a week or something, and everything is good. But it's not really, because it changes. The design changes and keeps changing. And this is just a minor part of a big web of interdependencies. And when something changes some place here, there are so many consequences, and it becomes really hard to deal with over time. Second example is what I call, what I see is not necessarily what you see. If I show you this graphic, what do you see? If I ask an architect, he would say, I see something like offices and some functional requirements. If I ask an indoor climate and energy engineer, he sees something like equipment load, solar heat gains, cooling demands, and stuff like that. If I ask an automation engineer, he doesn't care about the last room there because it has a thermal valve and therefore controls itself. But the two others are controlled zones where he has a set point temperature, some sensor that observes this temperature, some controlled device, and an actuator he can open or close to control the flow and thereby impact the temperature. He also has another control system, being the water that is being circulated, and it's very similar. The HVAC engineer, that would be me, sees something completely different. He sees the size of the radiators that should be able to fulfill the heating demand, flows in the system, pressure drops, velocities, putting valves or places to distribute the flow and to make it possible to do maintenance. So in my opinion, the BIM tools we have today, they don't really comply with this. So if one person initially creates something, it exists in that very model, and if other people are going to make some, attach some new attributes to the components in that model, it's not really possible. So that brings me to the research problem. Initially I thought, okay, so how to provide a web-based infrastructure for building data that allows a shared distributed data set to grow organically with the construction project, thereby providing insights and traceability as changes occur in a form that is consumable and extensible by any authorized agent involved in the project. And in this case, an agent is a software that acts on the behalf of some user. Okay, so back to some theory here. Where did we start with computation in the AEC industry? First we had computer-aided design, CAD, basically digitizing pen drawings. Next step was project websites that allowed us to store documents online, so anybody could go and download the latest state of the project documentation, which was pretty strong. You could attach metadata to it, such as who created it, at what time, what revision are we in. And then came building information modeling. There exist some different definitions of what building information modeling is. This one is from the ISO standard for information delivery manuals, stating that building information modeling provides a concept for designing and displaying information required in the design, construction, and operation of constructed facilities. And this other one is very commonly used also. It's from the BIM handbook, and it characterizes it as a modeling technology and associated set of processes to produce, communicate, and analyze building models. So it's not just technology, it's technology and methodology together. So it's kind of a complex size, but yeah, that's where it is. So what's the current state of this BIM? We have an open format which is published and maintained by Building Smart, called the Industry Foundation Classes. This is a data format, data model, and an open file format. It comes out of something called STEP, Standard for the Exchange of Product and Model Data. And often we describe it in a language, in a schema called Express. There are some shortcomings that I can find in the literature with IFC. One is that, this is by Mann Sachs, it's only used for exchange between BIM software that internally operate on proprietary data structures. So that means that in practice, it's basically read-only. But it stores the whole data model still with all the interdependencies and stuff, but it doesn't necessarily give us the interoperability we wish to have. Second point here is by Powles. There is a strong focus on geometry while the demands for knowledge capture are not adequately met. We have a third one here. No standardized query language to receive the data contained in a BIM model. You can open an IFC file in a proprietary software like Solibri, and they make an internal data model that you can access through their query language, but there's no open query language. And again, Express, as Zhang et al. States here, is not very widely used outside in the engineering domain. So not many general purpose tools support it. Like, no REST API just reads Express right away, and it's very hard to put into Excel. So something about the current state of BIM. These are some different maturity stages that are defined in the PAS 1192. And you can see that we have, on the very low maturity level, is CAD. And then when we move up, we get these object-oriented models. And level 2, file-based collaboration and library management, that's where we are today. Anything above the red line is future, and that's what we're dealing with in our research. But they deal with what they call integrated web services. Some call it semantically enriched integrated models that live on different servers, where you're able to just say, I just want to see the beams and I want to see the walls, and I don't care who built them initially, and if it's stored on the architects or the structural engineers' machines, I just want to access it. Okay, and then we see some developments in BIM in the cloud. So first I need to just go into what is the cloud really. In the cloud we operate with what we call RESTful APIs or web services. REST stands for Representational State Transfer. What it basically is, it's a machine sitting somewhere where you can say, send some requests and say, give me some data. Here is some data, store it somewhere safely. Update this set of data or delete this data. Or you could also fire something that is more complex and sets a bunch of operations, starts a bunch of operations, but that is basically what it is. So BIM in the cloud. We have some solutions available. Some are proprietary, like Autodesk. They have a lot of products. They operate in many different industries. And of course, they can make a closed system where this all works together. But they don't talk very nicely with the rest of the world. And is this really what we want to see, a monopoly like this? In my opinion, it shouldn't go that way. Then we have some more open, like Flux by Google. It was initially started by Google. And it was also initially free, but at some point, the idea with it was basically that you could take some geometry from one software, let's say SketchUp, then you could send it to their server where they did some operations on it to turn it into a neutral format, and again convert it all to the other format so you could see it in Revit. And this is all great, but the problem is that, it doesn't exist anymore, and if you put all your effort into that system, then all your effort is dead now. There are also some solutions that are fully open, like this one. This is called, what is it called again? Yeah, Speckle. Speckle works. And they're doing pretty much the same thing, and they're opening it completely. So you can take their server, you can download it, you can put it in the basement of your company, and you can do these things. But still, it depends on their internal schema. And if that's not updated, it's not really easy to go with. Then we have something like the BIM server, which is again completely open, and you can put an IFC file in there, and it parses it and puts it into a key value database that they have, or that you basically serve yourself, and it's open through a REST API, so you can access all the data in there, and it uses the IFC schema, but it could also use any other schema, so it says in the documentation. And also, so if we have something new tomorrow, it can deal with that. But IFC is the data model, and IFC is an open format, and this is good. Okay, so we agree that in order to have these open systems that talk together, what we need is a common language. And we have all these different standardization organizations that makes these languages. OGC works with GIS, geospatial data, building smart with buildings, Dansk Standard for a lot of the stuff that we do with buildings, and then we have SEN and ISO standards that for structural demands and stuff like that, structural codes and stuff like that. But the problem is that those are all open standards that very much evolve around their own closed world. So a building is both defined in the Open Geospatial Consortium and in Building Smart, and they don't relate to each other. So if you have something GIS that you want to describe with your BIM model, it's not very easy. And you can say, what approach should you then take to move out of this? We have a very much of a top-down approach where someone says, this is how the world looks like, but with something like Speckle works, we see more of a community-driven thing where people say, this is what we need. So how do we make these two worlds talk together? Fortunately, back in 2001, Tim Berners-Lee, the inventor of the World Wide Web, published this article about the semantic web. And he defined it as a new form of web content that is meaningful to computers, which will unleash a revolution of new possibilities. We're yet to see that revolution, though, but the technology is there, and it's tested and it's used. Okay, so what this can actually do is that That allows us to just say, okay, so you define some terminology over there that makes sense to you. I define mine over here, but I can see that those two terms are very related. We link them together, and I say this is the same as this. This is a more generic term for this, and stuff like that, meaning that we have collaboration between those. W3C has what they call the resource description framework, which is the data model that is used for the semantic web. How you model data is basically in what we call triples. A triple consists of a subject, a predicate, and an object. So that could, for instance, be some very specific wall, 002, has window 022. Or Mads has mother Dorte who's sitting there. Something like that. And together, this builds a knowledge graph. A knowledge graph is what we see here. This is an image I stole from Amazon Neptune. This is their graph store. And what you see is both what we call terminology and what we call assumptions. So the A box layer and the T box layer. So the Eiffel Tower, for instance, that's data, that's assertions, that's a tangible thing, something we can go and touch. But the fact that it's a place, that's terminology. A place is a class. Many things are places. DTU is a place. Bill, Alice, and Bob, they're all persons. Person is a class, is a relationship, that's also terminology. And the fact that Bill and Alice visited Eiffel Tower, that's also terminology that's used there. So I built this tool called the Sparkle Visualizer because this was quite hard for me to communicate to people. So basically what you see is that I modeled all this in these triples. Eiffel Tower is a place, Paris is a city, Eiffel Tower is located in Paris, Alice visited Eiffel Tower and stuff like that. And you can see, because people are not very confident with the graphs, that what you can do is actually that you go in and you make a query. Can I make this larger? Can you see it? Yeah, okay, now you definitely can. Okay, so you basically see, I need to look for something which is a person. And that something visited Eiffel Tower. And then I want to return every unique instances of that. In this case, I just call it node A. And you see if I fire that query, I get some results back. And that's only the places in the graph where they find a match. So that's only Bill and Alice. So that's how you go and look up information in this graph structure. Then we have what we call linked data. There is this confusion between linked data and semantic web. Linked data is basically these 4 rules. Linked data states that you need to use what's called unique resource identifiers to name anything. A URL or web address is a unique resource identifier. It also says that you should use HTTP URIs. So those are the ones that we use in our web browser. Because then people can look it up. So if you look up my unique URI, you'll find all information about me. Who are my friends? Where do I work? If you have the authorization to do so. And when someone looks up something, then you should provide some information that is valid. And then you should include links to other URIs so that they can discover more things. So the Eiffel Tower, when you look up that thing, then point to Wikipedia where it's explained how tall it is and all that stuff. Okay, so this is what it looks like. Not linked data is the syntax you saw in the top in the tool. Eiffel Tower is a place. Linked data is where you use full URIs for things. Now I just use some random URI, some knowledgegraph.org/resources/Eiffel Tower. That should preferably be a namespace that I own so I can show people something useful when they look it up. Then this is the RDF schema, or the RDF description actually saying it's an RDF type. And then schema.org is Google, Bing, and Yahoo who went together and say, we need to make sure that we use the same terms to name things. So something is a place, something is a museum. So it's basically a dictionary or a vocabulary of some settled words, and place is one of them. So now so it's a schema.org place is way more specific than it's just a place, because they have really defined what it is. And then often we use this turtle serialization where you can see instance, inst, is just a prefix for that long thing. So inst Eiffel Tower is the same thing as there. A is basically a shortcut for RDF type because you use it very often. And then schema place because it's a schema.org place. So that's what it looks like. The cool thing about this, and what you just saw there, was that I had one data set that was described both with RDF, with my own namespace, and with schema.org. So one data set can be described with concepts from different schemas. So my data set can be described with OGC and with Building Smart and with Dansk Standard at the same time, or Cunego classification system. The data set itself can also be described in different namespaces, meaning that the architect can describe part of it, the engineer can describe part of it, the client can describe part of it. Ontologies are more than just schemas. They also provide logic for reasoning. I don't want to go too deep into this because I don't have time for that. But I could, for instance, say that knows is a symmetric property. So if A knows B, then B also knows A. And the computer can infer this even though the data set is incomplete. Okay, then something about BIM and linked data. So these two things together. So back in 2005, Bates actually proposed that IFC was turned into this ontology version, IFC OWL, and it was formalized by Peter Powles and company later in 2016. There's also been some efforts where it was an IFC file that was basically extended with some linked data, and then there exists a lot of other work on very discipline-specific things like Internet of Things, smart cities and stuff like that. So, based on this, to my research questions. The primary research questions is how to utilize semantic web technologies to make assertions about a building, its properties, and the interdependencies between these in a manner that allows for change management and enhances transparency using widely adopted ontologies in the extent that these are available and what additional terminology is needed. First question here, I have 3 sub-questions that basically take this and boils it down a bit more. So what existing ontologies can be used to establish this common platform for an interdisciplinary information exchange in the AEC industry, and is there a need to extend these? How is it possible to get information from the BIM authoring tools used today, like Revit and Archicad, to the new platform? And research question 3, when describing a project using the common platform, how is it possible to capture design information as well as interdependencies while allowing them to change and evolve? The methodology I set up for this was something like this. We want to build this big knowledge graph. We need some terminology to describe the building, something for HVAC and ICE, indoor climate and energy, that extends this, and then something over here where we can handle the advanced properties that aligns with that, and we needed to an enabler to connect to the legacy software and also to build on top of it, simplified to something like this. So some building terminology, some enablers, some property terminology. So this would be my first research task, this would be my second research task, and this would be my third research task. An ontology then, an ontology specification described by Hoekstra here, is about reaching consensus on the meaning of terms, and therefore it becomes a social activity. So the way I approached this was through more of like a prototyping approach. Identify some requirements, develop a prototype, evaluate the prototype, revise the prototype, and then I was so fortunate to sit in Niros where I could talk to my colleagues about this how this worked. And also very early I got involved in this linked building data community group where we at some point had bi-weekly meetings, and we evaluated this and went to workshops like linked data in architecture and construction and had panel debates, and it evolved. Okay, so first research task was about this ontology for building information. The building topology ontology bot. We made this big survey initially where we saw, okay, so there exist some ontologies that are very generic. Some of them are focused entirely on buildings. Some of them are focused on smart cities. Some of them are focused on systems. Some on smart homes. All of these things are related to buildings. But we saw that they redundantly describe the same concept of a building, story, room, and an element. And it is possible to align ontologies and say this term is equivalent to that term. But when we have a lot of different ontologies all describing the same things, It will be a nightmare to go and align them all. So we thought we need something in the middle here. We need something very, very simple that only describes the core elements of a building that then can be extended for any given domain. So the initial version of BOT only had these 4 classes. A building could have stories, stories could have spaces, spaces could have adjacency to or contain elements. And anytime some of this was present, then it was inherited that the building also had the element, the story also had the element, and the space also had the element. So if a space of a story of a building, like a transitive property. Babushka-Doll principle. Then later it growed a bit, but also to allow more descriptions. So we used just one class for a spatial division being just a zone. And then we had these subclasses, the site, the building, the story, and the space. Site was new because we wanted to also describe university campuses or hospital campuses. Then we have elements, and then elements is basically anything that's tangible in the building. And an interface, which is anytime you want to quantify the relationship between any of those. Elements can then have sub-elements. Zones can contain zones, be adjacent to zones, or intersect with zones. The same with the zone. A zone can contain elements, it can have adjacency to elements, and it can intersect elements. And all these have a super property called has element, because sometimes it's just nice to have this simple property that you can query for. But it's not supposed to be stated explicitly. Okay, so BOT zones first. If we have a building like this, then in BOT it basically looks something like this. The site has a building, the building has a story, story has a space, space then again has a thermal zone inside of it. So in this way, zone is a way that you can aggregate or you can group, you can aggregate or you can subdivide zones. So you can use it for thermal zones, or you could use it to delivery zones for a construction manager or something like that. And it has this Babushka-Doll principle stating that the site also, of course, includes the space that is concluded in the building, which is included in the story and stuff there. Then later, we also have this possibility of describing adjacencies between spaces. And it was later discussed that we also needed something to describe something like a stairwell that intersects different levels of the building. And this is really nice because we have different interpretations of what we see. The architect only deals with what is below the suspended ceilings. Fire engineer also cares about what's above. Thermal engineer wants to subdivide for future use of the building. Sprinkling has special requirements for what is above the suspended ceiling. For lighting, you want to control something that is near the facade with the windows in a different way. Then we have BOT element. Same principle. If a BOT element is contained inside a space of the building, it's also contained in all the bigger boxes. BOT interfaces. We had this situation, since I deal with indoor climate and energy. We have these two zones. They're both adjacent to the wall. Where do we put the heat transfer area? So the concept was here that we, instead of just saying space has adjacent element, then you can put an interface between it and say the space is an interface of both of those, and that way you're able to quantify it. So then we have a situation more like this. So you can put the surface resistance there, you can put the area there. Great. And it would look something like this. The interface is an interface of the zone and an interface of the wall, and the same for the other one. Another situation where this would be useful would be a pipe going through several different spaces. How to express the relation to the different spaces, because then we could add thermal insulation automatically just by query, just to say if you're in a heated room, then this is what you need. If you're in an unheated room, this is what you need. Or basically just look at the temperature in the zone that you're going through, and that is the reasoning you use when you add your insulation. So that would look something like this. Then BOT is supposed to be extended because BOT is very simple. So if we have something like this, we can use subtyping. That's one method for doing it. So we have something which we know is a heater. And at the terminology side, we might have a flow systems ontology defining what is a heater. This is a heater. And that's the subclass of a BOT element, meaning that if I say my heater, if I say that my heater is a flow systems ontology heater, then because that is a subclass of BOT element, then it's automatically inferred that it's also a bot element. And that's handled by reasoning, which is done in most standardized triple stores that you can buy off the shelf. Then we have subtyping with bot properties. This is another approach. Say, okay, I want to make my own relationship called heated by, which is a subproperty of contains element, but it has another range. It doesn't just have bot element as a range. It's always a flow systems ontology heater that heats a space. So if I say my space is heated by, then a lot of things happen. Then because contains element is the super property, then that is inferred. The fact that it's a heater is inferred, and the fact that it's a bot element is also inferred. So even though my dataset doesn't contain this, it's automatically inferred. And if we talk about, there's been lots of discussions about this. What about product catalogs? Should we just subclass every product on the planet as a subclass of bot product? And we don't think that approach is valid. So say you have something in your building, which is a product refrigerator. Then just the very moment that this product exists in the context of the building, then it becomes a bot element. And those are some of the mechanisms that exist inside of the ontology. Research task 2, connecting to legacy software. So the first idea here was we have semantics in RDF, but we also want to see some geometry so people can actually be blown away by this and understand this. So I showed this prototype at Building Smart Summit in London 2 years ago. And basically what it has is that the geometry is just showed using the internal rendering engine that's part of Forge. So that's all living on their servers, and I don't have any insights in any of that stuff. But beside from that, I also have my triple store that contains all these triples. So I can go and say, give me everything that is adjacent to this space and give it to me in a list. And that was pretty nice because then people could actually see how this stuff worked. Yeah. Just have to click. Sorry, I lost something here. What's this one? Okay. The next thing was we don't need to necessarily have this geometry in order to represent some resource. And that was also pretty hard to tell people. Like, okay, so we can have the spaces without having the geometry, because then you can start talking about them, and this is nice. But we also said, okay, geometry is just a property like any other thing, or an attribute like any other thing that you can attach. So say in your data set, you have something which is a space, which is then also a zone. It has a name, both in Danish and in English and all that stuff. That's part of the RDF schema. But you could also say it has a space boundary, and it also has this 3D model, and could also have 10 3D models at different levels of detail or for different purposes. Then I developed this prototype to show how this worked. So basically here, asking for all the levels in the building, all the stories in the building. When you click a story, get all the spaces, get all the room boundaries. I'm not sure how it doesn't work here, but fortunately I also opened it here. So basically you can click a space, you get the adjacent elements, you click it, you get back, you get the adjacent elements. Or you want to have all the windows in the building, you want to see all the elements in the building, you want to see everything that is contained inside something else. So basically that. Okay, next experiment was integrating with sensor observations. Okay, so we had this Revit model of Navitas, it's a building in Aarhus, in Revit. Wrote a parser so we could parse it to bot. So we got this part, it's a building, it has some levels, it has some spaces, the spaces have some names, they have some 3D models, we've described them in OBJ, space boundaries in well-known text. Then we had these sensor readings in spreadsheets basically. There already exists an ontology for that, that's a W3C recommendation, so why not just use that? They already describe what a sensor is and what is an observable property and an observation. So basically all the sensors and what they observed and all the observations was modeled in that way. We had this vision that the engineer basically just described that this space has a sensor and all that stuff without even drawing it because it doesn't need to have geometry. And then when you put all this stuff together, you get all the semantics from bot and all the inference rules, meaning that we can get all this nice stuff with the containment and stuff. And then, again, develop the prototype to show how it worked. So something like, give me some story here, then give me all the maximum temperatures and color grade them based on how the temperature is. When you then click a space, then give me the sensors contained there, and give me all the readings from these sensors. So very simple way of showing how you can navigate such a knowledge graph in a user interface. Okay, then research task 3, dealing with these evolving interdependent design properties. The ontology for property management, OPM. We often describe these projects as going through planning, from planning through design to construction, but the situation is more like this if you're from the industry and you know how it works. So my concern, what I was wondering was, okay, so if we have a window that at some point in time looks like this, and then it looks like this some other point in time, is it still the same window we're talking about? In London, I also showed this illustration. And the idea here was that the architect, that's the black thing there, draws the wall. The indoor climate engineer extends that data set and puts some thermal properties on a heat transmission surface, and the structural engineer add a reinforcement definition over there. Then we have a problem if that wall does not exist and is just taken out of the project. So then I think we would rather that it's just the same wall with a new property. So resources shouldn't be deleted. So the idea was that instead, okay, so it's just window 325, but with some changed attributes. Okay, and this can be handled with 3 different levels. The most simple way of describing some attribute in RDF is just a data type property. So window has width 1800 millimeters. But then it's not possible to describe who made this and why did he make it and all that stuff, adding metadata to it. But what we can instead do is that we can put an intermediate node in there and say, okay, so the window has a property and that property has a value, and it was generated at a time and it was attributed to a person. And all these terms I use here is from another ontology called the provenance ontology. So again, something that already exists and is widely used. But what if we wanted to change over time and to be able to capture that? Then we need another layer. And how we did that was that we implemented or we introduced the concept of property states. So a property can change state over time. So you see first, I defined it as 1200 millimeters, and then Christian at some other time defined now it's 1800 millimeters because he changed it. Of course, this is not something you model yourself. The tools are taking care of it, but it's a data model that takes care of it. But what you can see is that only one of them is classified as the current property state. Okay, so how does it work? Say we have some property and it has a state to it. Now we want to add a new state. Okay, we delete the current property state from the old one, infer a new one, and that one is classified as the new current property state. And when we do the query, we basically ask for the current property state when we ask for the most recent version. If we want to delete it, we add a new state, which we call a deleted. We classify it as OPM deleted, and that's the current property state. So in our query, we can take care of, we don't want to see the deleted. Or if we do want to see the deleted, we can do that. And then you can restore it through a basic query. Then we add the concepts of property reliability. I don't want to go down that road because it's probably too much, but in a paper I presented how this could be used to say that a property is a requirement of a future property. So for instance, the area of this space should be between 20 and 30 square meters. Or it can be an assumption. In engineering, we very often do assumptions in order to progress with the design. So we assume that the U value will be 0.25 watts per square meter Kelvin. It can also be a confirmed value. So at some point you might decide that the superstructure of the project is locked. It won't change. So according to this document, it's locked, meaning that the people working with these elements know that it's probably not going to change. Wouldn't go down that road. Then we have derived properties, and this is more interesting, but it's also very complex. So, for instance, if we have a space that has an infiltration heat loss and a transmission heat loss, we could say, and we can explicitly state now, that the heating demand is the sum of those two things, and it's derived particularly from that very state of that property and that very state of that property. So if some of the arguments change, I will be aware of that, and I will be able to go and make adjustments. I could also use another part of OPM, which is a formal way of describing what a calculation is. So what you can describe is, what is the inferred property? What is the expression? Here it's those two variables added together, and then some argument paths. The argument paths are basically stating from where I'm standing in the graph, I need to find something that has both a transmission heat loss and an infiltration heat loss, and those are the two variables that you add together and infer the new property. And this was also implemented in a REST API. An example of this would be something like this again. If we go back to the example with the heat transfer through the wall. So we make, again, an extension of BOT called the ICE ontology with thermal environments and thermal envelope. So those are the unique things that we want to specify here. Then the interfaces are not specific enough for our purpose. We want to know what interior it touches, what exterior it touches, and what element it represents, because that's where we're finding the U value, and those places are where we're finding the temperature sets. Looks something like this. Won't go into that now. And then we can make our project-specific ontology, where we say, okay, in our project, we have a class that we call a heated room. A heated room always has some properties, for example, and the same, we have a wall type B, and this is how we see a wall type B. So independent on how the architect defined the class of the wall, we can say, from our point of view, it's an engineering wall, it's a wall type B. Okay, and that looks something like this. And then we can actually make property restrictions and say, every time I have a heated room, on the property design ambient temperature, it needs to have the value 20 degrees Celsius. And the same for outdoors, that's minus 12. And the wall type B always has 0.25 watts per square meter Kelvin. That will automatically be inherited to all the instances of this class. And this is also taken care of by reasoning. And you can make more of these calculations. So the UA is the product of U and A, and you find it like this. The temperature difference is the difference between the two temperatures that you find by finding the interior and exterior. Then you can take the product of the UA and the delta T, and that gives you the total heat transfer rate through that segment. Now you have that inferred to all the segments. Next thing is to take all the rooms and say, how many of these are you facing? Sum them up, and then infer that, which gives you this big tree that you can also calculate quite easily through the graph structure, because you know all these different interdependencies. And I actually built a REST API called OPM REST, where these calculations, since they have a URI, when you send a post request to the URI, it actually goes and checks. It knows all the properties of the calculation. So it checks for everything, every place where that argument path is applicable, and then it infers the first inferred property if it can do so. A put does the same thing, but it looks for all the places where the property is already inferred, but where one or more of the arguments has changed, and then it updates it with the new value. But it could also be that you have a microservice where you have such a URI that basically runs a whole Energy Plus simulation, or a radiant simulation, or a fine element simulation, or whatever. Or you could just have something listening for changes and saying, when this changes, then I need to redo this calculation and infer the new results. So all this stuff I'm talking about actually exists in this client application that you can go and test out yourself. Yeah. So implications and conclusions. Research questions revisited. The first one, we need some ontology to describe what a building is and what and do we need to extend them and stuff like that. So there exist a lot of domain ontologies in the scope of Internet of Things, in the scope of GIS, in the scope of many things around our buildings. SSN and SOAS is a W3C recommendation, so why not use it? And BOT is usable as glue. And later I'll show you why I can prove that. Research question 2, connecting to legacy software. Wrote a Revit exporter, so it's possible to go from Revit to this format. They have an open API, so it's possible. Another researcher, Jyrki Oraskari, wrote an IFC to link building data converter, so now it's possible to go from an IFC file. It also supports geometry now. And I have shown all these small prototype apps, so it's also possible to have these web applications that can show the content of these knowledge graphs. Third question, so that's something about capture design information as well as interdependencies while allowing changes to evolve. That's OPM. Contributions to academia. The intention was to provide some simple, extensible ontology for knowledge representation in the AEC industry. And this is the current state of papers that refer to BOT. So you can see in GIS and geometry, in compliance checking, in life cycle analysis, in damage control or classification of damages, information retrieval, products, acoustics, general AEC, IoT, building management systems, indoor climate and energy, human experience, and facility management. The project is very much alive on ResearchGate. These are the followers, researchers from around the world. Sparkle Visualizer is very much being used around the world. Also, more than 50 countries have activity, and actually where the sessions are running more than 5 minutes, so people are using it. And more than 700 unique users have used it so far. I still have some work which is in review. This one over here, but the building topology ontology of the W3C Link Building Data Group was submitted to the Semantic Web Journal on May 15th. And this other one, managing integrated project information in AEC Knowledge Graph, was submitted to Automation and Construction in January 14 first time, and a revision was submitted on June 23rd. But the responses from the reviewers was really, really positive. That was the reason why I developed that client application. Contributions to the industry. In Niros, we have this idea that we have all these different data sets that are sitting there, and we want to have some glue that can connect them somehow. So we developed this kind of framework where we have the data sitting there in the top. Then we want to provide some structure to it, and then we want to make all these small applications, very, very narrow scoped applications that is just has one purpose, that the consultant can use as an interface to the knowledge graph in order to develop, to deliver consultancy to our clients. And these applications can either be just something that makes documentation, like a diagram. Why is a diagram something you draw? Why is it not something that you just generate out of data? You could also visualize it to provide some insights, but it could also be tools where the engineer can actually grow the database. This is an example of the tools we developed, and this is using OPM in the background. So every day, this is Børneriget, a big hospital project that we're working on in central Copenhagen. So what you're seeing here is that when I move the slider, every 24 hours, we pass the whole model. On the server, we check, are there any differences from how it looked like yesterday? If there are, we add new property states with OPM. And what we're doing here is that we're saying, okay, what was the state at the first period? What was the state at the last period? Did the area change? How much did it change? That's a color gradient. Is it new? That's when it's green. And then the two space boundaries are laid on top of each other, and you can see the dashed lines here indicate that it's the old one. So that's one example of a tool. Future outlook. I did some preliminary work on flow systems, a flow system ontology. It stopped when I started working on the OPM because I found that we needed these mechanisms in order to progress. Fortunately, there is a new PhD working in this domain called Ali, and I'm fortunate to also supervise him. But yeah, we had some preliminary work in this. The idea is also like, so the fact that a pipe feeds a T, which feeds another pipe, which again feeds some consumer. If you make feeds a transitive property, you could also just stand any particular place in the graph and say, I want all the consumers that this pipe feeds indirectly. And then I want the sum of the flow. and then I want to calculate the size of it and infer that and stuff. So an explicit structure for pipe systems, which would be pretty nice, especially for retrofitting of buildings and stuff, if it could just recalibrate. Then I had these thoughts of how do we go from research to standard? And again, if we have this top-down, bottom-up approach, I think very much that if universities and companies engage in growing and building these ontologies, like in Neros, we're building an ontology to describe the world, because just internally in a company with 2,500 people, we use very many different terms for the same thing. And if we can just solve that internally, then we really stepped up. And if we share that ontology, why not just pick it up as a national standard, or at least refine it and use it as a national standard? For us, it makes a lot of sense if people reuse it, because then we have greater interoperability. And why not utilize that we have so many bright students? This is some work actually by Peter Powles, and that has been presented by him and Sigve and Jakob Beetz, where the idea is actually to make the IFC schema, so it was presented at Building Smart, actually make the IFC schema something like this, so use this modular approach. Also, the bot ontology does not need to necessarily live on GitHub. It should be pushed to some higher standard organization. It's also best, you say everyone can develop their own ontologies, but you should always use the ontologies that have, of course, higher, what could you call it, like, higher acceptance, so more people use it, and also that is maybe developed by some organization that has some substance to it, like OGC or Building Smart. Then I have a little something about true decentralization. Can I go down that road? Very, okay. Tim Berners-Lee, the inventor of the World Wide Web, who gave me this sticker, and Ruben Verboe, on the right-hand side, also from Ghent University, they have this new vision of a decentralized web. What they have come to a conclusion that now we have a web. The idea was that you have a web where people can publish and they can extend each other's documents. So a document can link to another document, a web of documents. Basically, it was invented at CERN back in the days for researchers to relate to each other's papers. But what it ended up being is big giants like Google and Facebook harvesting lots of data, and we're typing everything in there, and we're putting it in their databases, but we don't own our own data anymore. So the idea would be that we all have our own personal data hubs, and the universities have data hubs, and companies have data hubs, and then a page like LinkedIn could basically be, I need to have access to that information from there, and there. Can you provide it to me? Yes, I can. And then we can make the view of your profile page there, for instance. Then instead of having these centralized web applications where your contact list and your pictures and your agenda live on Facebook, and your LinkedIn has your contact list and your agenda, then we would have something more like, I have a photo gallery app that can read my pictures. My social feed can read both my pictures, my agenda, and my contact list and meeting scheduler and stuff like that. And I tried to make kind of a reference to our industry and say we have Revit that has the geometry and the plan drawings and the room schedules and everything in this big box, monolithic system. Then we have Rhino that we tend to use when we make something more complex. And then we have SketchUp when we start the project. So we have a lot of redundancies there. How about having a facade study design tool and a scheduling tool and a design for manufacturing, design for assembly tool or something like that instead? Or my prototype there was in a heater sizing application where, like, why not get the codes from one place, and authorities part could be something, architects part could have the geometry, clients' requirements for the spaces, and then the engineers' properties, and all that stuff together adds up and becomes the heater sizing, basically. So final words, minimal extendable core ontology, that is apparently a valid approach. The semantic web can be the platform for a database information exchange. OPM provides the terminology. We still need to see if it's a viable way to handle interdependencies, especially in regard to how it scales. Proof of concept applications were developed, but the most important contributions of my work here, that's the ontologies, because that's what's providing the schematics that people can use and build great tools on top of. And that's what I had. Woo. And of course, a great thank you to all the people who followed me and helped me, supervised me, taught me,